Imagine a dead star, barely 20 kilometers across, drifting through the darkness of space. No fusion burns in its core. No light pours from its surface the way our sun shines. And yet, this object is one of the most violent things in the known universe. Because threaded through every layer of its impossibly dense matter is a magnetic field so powerful it reshapes the structure of atoms themselves. It warps the vacuum of empty space. It stores enough energy to crack the star's own crust wide open and unleash bursts of radiation detectable across the entire galaxy. This is a magnetar, and tonight we're going inside one. Because what happens in there, where the strongest magnetic fields in nature meet the densest matter in existence, is one of the most extreme stories physics has ever tried to tell. Before we get into this, if you find these deep explorations of the universe interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let me start with something you already understand. Magnets. You have played with them since you were a child. You have stuck them on your refrigerator door. You have felt that invisible pull when two magnets snap together in your hands. That little tug reaching through empty air as though the space between them were not really empty at all. That force, that invisible reach, is a magnetic field. Every magnet produces one. It extends outward into the surrounding space, influencing anything sensitive to it. Iron filings, compass needles, other magnets. The field is invisible, but it is absolutely real. You can feel it in your fingers. And like anything real, it has strength. Some magnetic fields are weak, some are strong, and some, as you are about to discover, are so far beyond strong that the word loses all meaning. The strength of a magnetic field is measured in units called Gauss, or in a larger unit called Tesla. 1 Tesla equals 10,000 Gauss. A typical refrigerator magnet produces a field of roughly 50 to 100 Gauss. That is enough to pin a piece of paper to your fridge, but not much more. It will not pull a spoon out of your hand. It will not affect the electronics in your pocket. It is a modest field doing a modest job. Now consider the magnetic field of the Earth itself. The field that makes your compass needle point north. The field that reaches tens of thousands of kilometers into space, forming an invisible shield called the magnetosphere that deflects the constant stream of charged particles flowing outward from the Sun. That field, the one protecting the entire planet and every living thing on it, measures roughly half a Gauss at the surface. Half a Gauss. The entire Earth, with its churning molten iron core, generating field lines that arch far out into space and loop back, produces a magnetic field weaker than the little magnet holding your grocery list to the refrigerator door. And yet Earth's field is essential for life as we know it. Without it, the solar wind would have gradually stripped away our atmosphere over billions of years, the way it stripped the atmosphere from Mars after Mars lost its own magnetic field. Earth's field has been our invisible guardian for most of the planet's history. But in terms of raw magnetic strength, it is feeble. It is almost immeasurably weak compared to what exists elsewhere in the universe. It barely registers on the scale we are about to climb. The Sun has a magnetic field as well. On average, the Sun's general background field is only a few Gauss, which might surprise you given how massive and energetic the Sun is. In many regions, the Sun's field is comparable to Earth's, but the Sun is not uniform. In active regions, particularly around sunspots, where magnetic field lines bunch together, twist, and punch through the solar surface, the field can climb to several thousand Gauss. Sunspot magnetic fields are powerful enough to suppress the normal convection of hot plasma rising from below, creating those dark, cooler patches you can see on the Sun's surface through a properly filtered telescope. And occasionally, When tangled magnetic field lines snap and reconnect violently, they release enormous bursts of energy we call solar flares. Events that can hurl billions of tons of charged particles toward Earth. These events are powered by magnetism. They are impressive and sometimes dangerous to our technology. But even a few thousand Gauss is modest by the standards of what nature is capable of producing. The Sun is magnetically active, but it is not magnetically extreme. Let us move now to human technology. If you have ever had an MRI scan at a hospital, you are lying inside one of the strongest magnets most people will ever encounter in their lives. A typical MRI machine generates a field of about 1.5 to 3 Tesla. In Gauss, that translates to 15,000 to 30,000 Gauss, roughly 30,000 to 60,000 times stronger than Earth's magnetic field at the surface. The machine uses that powerful field to align hydrogen nuclei in your body, then detects the faint signals those nuclei emit as they relax back to their natural state, producing detailed images of your organs and tissues without any surgery. Some people report a metallic taste in their mouth inside an MRI bore. Others feel slight dizziness or a strange warmth. That is the magnetic field physically interacting with the conductive fluids in your body at a level you can actually perceive. But MRI magnets are not even close to the strongest magnets humans have built. The most powerful sustained magnetic field ever produced in a laboratory is about 45 Tesla, generated by hybrid magnets at the National High Magnetic Field Laboratory in Tallahassee, Florida. 45 Tesla is 450,000 Gauss. These magnets require enormous amounts of electrical power, sophisticated cooling systems, and carefully engineered structures to contain the immense forces the field generates on its own coils. For very brief moments, using pulsed magnets that fire enormous currents through specially designed coils, researchers have achieved fields exceeding 1200 Tesla. But these pulses last only tiny fractions of a second because the magnetic forces physically tear the coils to pieces. The strongest, reliable, sustained magnetic field our entire species has ever generated, with all of our technology and engineering, is about 45 Tesla. Keep that number in your mind, because we are about to leave it behind completely. An ordinary neutron star, and I say ordinary as though there is anything ordinary about a neutron star, generates a magnetic field on the order of 100 million Tesla. Let me say that again. 100 million Tesla. That is roughly 1 trillion Gauss. A typical neutron star, the kind astronomers would describe as unremarkable, produces a magnetic field about 2 million times stronger than the most powerful sustained magnet humans have ever built in a laboratory. 2 million times stronger. And the neutron star does not produce this field with engineered coils and massive power supplies. It produces it naturally, simply as a consequence of what it is and how it was born. We need to talk briefly about what a neutron star actually is, because you cannot understand a magnetar without understanding the object it begins as. A neutron star is what remains after a massive star dies. When a star significantly heavier than the Sun, typically 8 or more times its mass, exhausts the nuclear fuel in its core and can no longer support itself against the inward pull of its own gravity, the core collapses. The outer layers of the star are blown outward in a supernova explosion, one of the most energetic events in the universe. But the core does not explode. The core falls inward, crushed by gravity so violently that the atoms making up the core are destroyed. Protons and electrons are forced together under immense pressure to form neutrons. What remains is a ball of neutron-rich matter roughly 20 kilometers across, about the width of a large city, containing more mass than the entire Sun. All of that stellar mass, material that once filled a volume millions of kilometers across, is now squeezed into a sphere you could almost drive across in 15 minutes on a highway. The density of this object is beyond anything in ordinary experience. A sugar cube-sized piece of neutron star material would weigh roughly 1 billion tons on Earth. If you could somehow place it on the ground, it would sink straight through the surface and keep going. The gravitational field at the surface is about 200 billion times stronger than Earth's. If you could somehow stand on a neutron star, which you obviously cannot because you would be instantly compressed into a thin film of matter, you would weigh as much as a small mountain. Light itself bends noticeably in the gravitational field. The star is so compact that general relativity, Einstein's theory of curved spacetime, becomes essential for describing its structure. Newtonian gravity is not sufficient. The neutron star exists in a regime where spacetime itself is significantly warped. Now here is a critical point for our story. During the collapse that creates a neutron star, something happens to the original star's magnetic field. The massive star that existed before the supernova had its own magnetic field, perhaps a relatively modest one by stellar standards. But as the core collapses, shrinking from a sphere thousands of kilometers wide down to a sphere just 20 kilometers across, the magnetic field lines are compressed along with the matter. This is a consequence of a principle called conservation of magnetic flux. Think of it this way. Imagine drawing parallel lines on the surface of a large rubber balloon. Now deflate that balloon down to the size of a marble. The lines get squeezed together. They crowd closer and closer as the surface shrinks. The density of lines per unit area increases enormously. The same principle, applied to the collapsing core of a dying star, takes a relatively modest stellar magnetic field and amplifies it by a factor of tens of thousands through compression alone. Combined with additional amplification processes operating during and shortly after the collapse, including convective motions and differential rotation in the newly formed neutron star, this is how a typical neutron star ends up with a surface magnetic field of about 1 trillion Gauss. But a magnetar is not a typical neutron star. A magnetar is a neutron star whose magnetic field is roughly 1,000 times stronger even than the field of an ordinary neutron star. Where a typical neutron star might have a surface field of about 1 trillion Gauss, a magnetar can carry a surface field of 1 quadrillion Gauss. That is 10 to the 15th power Gauss, up to roughly 100 billion Tesla. This is not a small enhancement. It is not 10% more. It is not double. It is a 1,000-fold leap beyond objects that already possess the strongest persistent magnetic fields of any common astrophysical source in the universe. Let me try to give you some sense of what this factor means. Earth's magnetic field is about half a Gauss. A magnetar's field can exceed 1 quadrillion Gauss. That is a ratio of roughly 2 quadrillion to 1. If Earth's magnetic field were represented by a single drop of water, a magnetar's field would be represented by something far exceeding all the water in Earth's oceans. The comparison barely works. Ratios this large are almost impossible to communicate because your everyday experience gives you nothing to map them onto. Nothing in your daily life differs from anything else by a factor of 2 quadrillion. No building is 2 quadrillion times taller than any other building. No sound is 2 quadrillion times louder. The number is so vast it becomes abstract. But the field is not abstract. It is real. And it has physical consequences that are extraordinary. At field strengths in the magnetar regime, the magnetic field stops being a background property of the environment and becomes a dominant force shaping the physics of everything nearby. Let me give you one more comparison to make the scale visceral, because numbers alone do not communicate what this field would actually do to the physical world around it. Imagine you could take a magnetar and somehow place it halfway between the Earth and the Moon. roughly 190,000 kilometers away. Ignore for a moment the gravitational consequences. Focus only on the magnetic field. At that distance, the magnetar's dipole field would have weakened enormously from its surface value, falling off with the cube of the distance ratio. And yet, even at that range, the residual field reaching Earth would still be roughly 150 Gauss, several hundred times stronger than Earth's natural magnetic field. Every compass on the planet would swing to point at the magnetar instead of the North Pole. Sensitive magnetic instruments would be driven off-scale. Navigation systems relying on geomagnetic reference would fail, and that is the field at 190,000 kilometers from the surface, diluted across a distance far greater than the diameter of the Earth itself. The surface field, where the physics we care about actually happens, is trillions of times stronger than what reaches Earth in this thought experiment. At a distance of roughly 1,000 kilometers from a magnetar's surface, still well within the magnetosphere, the field is strong enough to be lethal to a human being, not through radiation, not through heat, but through pure magnetic force acting on the matter in your body. Water molecules, which make up roughly 60% of your body mass, are weakly diamagnetic. They are very slightly repelled by magnetic fields. Under normal conditions, this effect is negligible. You could stand next to the most powerful MRI machine on Earth and feel nothing from diamagnetic repulsion. But in a field of millions of Tesla, the diamagnetic force on water becomes enormous. Your body would be distorted and ultimately torn apart at a molecular level. The magnetic field would exert different forces on different tissues depending on their magnetic susceptibility, stretching and compressing your body in ways no biological structure could survive. Long before you reached the surface of a magnetar, long before you encountered the crushing gravity or the intense radiation, the magnetic field alone would have killed you and disassembled the molecules you were made of. Near the surface of a magnetar, the field is powerful enough to distort the shapes of atoms. In a field exceeding 100 million Tesla, the electron clouds around atoms do not form the familiar spherical or lobed orbitals you may have learned about in chemistry class. Instead, the magnetic force squeezes electrons into tight, narrow cylinders aligned with the field lines. Atoms become elongated, stretched along the direction of the magnetic field, and compressed in every other direction. They stop being roughly spherical and become needle-like. Chemistry as we understand it ceases to function in this environment. The way electrons arrange themselves, the way atoms bond to form molecules, all of it is overwhelmed by the magnetic field. The field dictates the geometry of matter itself, and the effects reach even further than the structure of atoms. Quantum electrodynamics, the theory that describes how light and charged particles interact, predicts that in sufficiently strong magnetic fields, the vacuum of empty space itself behaves differently. Normally, light travels through a vacuum with no preferred direction, no dependence on polarization. The vacuum is the same in all directions. But near a magnetar, the magnetic field is so intense that the vacuum becomes birefringent. It bends light differently depending on the polarization of the photon relative to the field direction. Empty space around a magnetar behaves almost like a crystal. This is not speculation. It is a firm prediction of established physics, and astronomers have found observational evidence consistent with this effect. We will return to these quantum effects later. So that is what a magnetar represents in terms of magnetic strength. An object at the absolute extreme of what nature produces, separated from anything familiar by such an enormous gap that comparisons become meaningless. But how did we discover that such objects exist? The answer begins not with magnets or magnetic theory, but with a sudden, blinding flash of gamma rays from deep space. On March 5, 1979, something extraordinary happened. a wave of high-energy gamma radiation struck several spacecraft scattered across the inner solar system. It hit them nearly simultaneously, registering on instruments aboard Soviet Venera probes, American satellites, and other detectors in the interplanetary network. The pulse was intense, far more powerful than anything these instruments had been designed to measure. Some detectors saturated completely, pegging their readings at maximum and losing information about the peak intensity. The burst arrived from the direction of the Large Magellanic Cloud, a small satellite galaxy of the Milky Way, located roughly 160,000 light-years from Earth. For a brief fraction of a second, this single source had become the most luminous gamma-ray emitter in the sky, outshining everything else in that part of the electromagnetic spectrum. At first, many scientists assumed it was a gamma-ray burst. These violent, one-time explosions had been detected since the late 1960s, and while their origins were not yet understood, their basic character was established. They were brief, they were catastrophically energetic, and they did not repeat. A source would flare once and then go silent forever. But as researchers analysed the March 1979 event more carefully over the following weeks and months, they noticed something that did not fit the gamma-ray burst template. The initial spike of emission was followed by a pulsating tail, a fading signal that oscillated with a regular period of about 8 seconds. That periodicity was a critical clue. Something was rotating once every 8 seconds and modulating the emission as it spun. And whatever this object was, it had just unleashed a blast of energy equivalent to what the Sun radiates over roughly 1,000 years, all compressed into a fraction of a second, from 160,000 light-years away. Then, over the years that followed, additional bursts were detected from other locations in the sky. These subsequent events were generally softer, less energetic than the extraordinary March 1979 flare, but they had a remarkable property. They repeated. The same sources would flare again and again, producing multiple bursts separated by days, weeks, or months. This was completely unlike classical gamma-ray bursts, which were always single, unrepeated events. These sources were persistent and active. They flared, went quiet, and then flared again. Some produced dozens of bursts over years of observation. Astronomers classified them as a new and distinct category of astrophysical source. They called them soft gamma repeaters, named for their softer energy spectrum compared to classical gamma-ray bursts and their defining habit of repeating. What made these sources even stranger was the sheer energy involved. Even the smaller, more common soft gamma repeater bursts released astonishing amounts of energy in fractions of a second, and the larger bursts exceeded what the Sun produces in an entire year. That energy emerged from a source smaller than a city, and it arrived in the form of gamma rays, the most energetic wavelength of light, photons carrying millions of times more energy per particle than the visible light your eyes detect. Whatever was producing these bursts was converting stored energy into radiation with an efficiency and violence that defied every known mechanism for neutron star emission at the time. Astronomers tried to explain the bursts using existing models. Perhaps the neutron star was accreting matter from an unseen companion, storing material on its surface until a thermonuclear runaway ignited, like the Type 1 X-ray bursts observed from other neutron stars in binary systems. But the spectra were wrong. Thermonuclear bursts produce softer radiation with characteristic thermal signatures. The soft gamma repeater bursts had harder spectra and very different temporal profiles. Perhaps the bursts were powered by the rotational energy of the neutron star, some exotic variant of the pulsar emission mechanism. But the energetics did not work. The observed rotation rates were too slow, the inferred rotational energy too modest to account for the burst luminosities. Every conventional explanation fell short. The energy had to be coming from somewhere, and the usual suspects, rotation, accretion, residual heat, could not supply enough of it quickly enough to match what the instruments were recording. Something else was powering these objects, a reservoir of energy that nobody had seriously considered as a dominant source for neutron star emission. It would take another decade before anyone identified what that reservoir was. By the late 1980s, a small handful of soft gamma repeater sources had been catalogued, and the puzzle had only deepened. The brevity and energetics of the bursts clearly pointed toward compact objects. The pulses were too short and too luminous to come from anything large. The periodic oscillations in some events indicated rotation. All of this pointed toward neutron stars. But every conventional mechanism for powering neutron star emission had been tried and had failed. The energy had to be coming from a reservoir nobody had seriously considered. Something was at work inside these objects that existing models simply could not account for. And identifying that something would require an entirely new way of thinking about what a neutron star could be. The breakthrough came in 1992, when two astrophysicists, Robert Duncan and Christopher Thompson, published a theoretical paper that would eventually reshape our understanding of neutron stars and these strange bursting sources. Duncan and Thompson proposed that certain neutron stars could be born with magnetic fields vastly stronger than those of ordinary neutron stars. Their argument centered on the first 10 to 20 seconds of a neutron star's life, the chaotic interval just after the core collapse, when the newborn star is still blisteringly hot, rapidly rotating, and violently convecting. They showed that if the proto-neutron star was spinning fast enough and convecting vigorously enough during that critical window, a dynamo process could operate inside it, amplifying the magnetic field to extraordinary levels through the churning motion of electrically conducting fluid. Not the trillion Gauss fields of typical neutron stars, but fields 1,000 times stronger. Fields reaching 1 quadrillion Gauss. They called these hypothetical objects magnetars. Duncan and Thompson demonstrated that if magnetars existed, their extreme magnetic fields would naturally and elegantly explain the soft gamma repeater phenomenon. The enormous energy stored in a magnetar strength field could be released violently when the field configuration evolved or rearranged itself, stressing and eventually cracking the neutron star's rigid crust, unleashing bursts of high-energy radiation in the process. The magnetic field itself was the energy reservoir, not rotation as in ordinary pulsars, not infalling matter from a companion star as in X-ray binary systems. The magnetic field alone stored enough energy to power repeated, powerful bursts across years and decades. The energy budget worked. The timescales matched. The theory was physically plausible and mathematically consistent. It was an elegant solution to a puzzle that had stumped astrophysicists for over a decade. But a theory is only a theory until observations confirm it. The confirmation came 6 years later in 1998. An astrophysicist named Krissa Kuveliotu and her colleagues used data from the Rossi X-ray Timing Explorer, a satellite designed to study rapid variations in X-ray sources, to measure the rotation period of a known soft gamma repeater source with extraordinary precision. More importantly, they measured how quickly that rotation was slowing down. This spin-down rate was the critical measurement. A neutron star spinning in a vacuum while carrying a strong magnetic field acts like a magnetic brake. The rotating field generates electromagnetic radiation that carries away rotational energy, gradually slowing the star. The stronger the field, the faster the spin down. By measuring the rate at which the soft gamma repeater was decelerating, Kuveliotu and her team could calculate the magnetic field strength directly. The result was remarkable. The implied field strength was on the order of 100 billion Tesla, squarely in the magnetar range that Duncan and Thompson had predicted. The theoretical framework was confirmed by direct observational measurement. Magnetars were real. Since that confirmation, our catalogue of known magnetars has grown steadily, but remains small. As of the most recent surveys, roughly 30 magnetars have been confirmed, with additional candidates awaiting verification through further observation. They are found almost exclusively through space-based X-ray and gamma-ray telescopes, because the radiation magnetars produce most intensely falls in wavelengths that Earth's atmosphere absorbs completely. You cannot observe a magnetar's characteristic high-energy emission from the ground. You need instruments in orbit, above the blanket of the atmosphere, equipped with detectors sensitive to X-ray and gamma-ray photons. Observatories like the Chandra X-ray Observatory, the XMM Newton satellite, and various gamma-ray missions have been essential tools for detecting and studying these objects. These telescopes can pinpoint the positions of magnetars in the sky, measure their pulse periods with high precision, track their spin-down rates over months and years, and monitor their bursting activity. Some magnetars remain relatively quiet for extended periods, emitting only a steady glow of X-rays, then suddenly erupt in a flurry of bursts before settling down again. Others pulse more regularly. The persistent X-ray emission is itself an important signature. Ordinary rotation-powered pulsars cannot produce the level of X-ray luminosity that magnetars exhibit. Something beyond rotational energy is powering that glow. In the magnetar model, the answer is straightforward. The magnetic field itself slowly decays over time, and the energy released by that decay heats the star's surface and interior, powering the persistent X-ray emission. The magnetar literally glows because its magnetic field is dying, gradually converting magnetic energy into heat and radiation. 30 confirmed objects might not sound like a large number, and it is not. The Milky Way contains an estimated 100 million to 1 billion neutron stars in total. Only a tiny fraction of those are magnetars, or more precisely, only a tiny fraction are currently in the active magnetar phase. This rarity is consistent with the Duncan-Thompson model. To create a magnetar, you need a very specific set of conditions at birth. The collapsing core has to be spinning rapidly enough and convecting vigorously enough during the first seconds of the neutron star's life to drive an efficient dynamo that amplifies the magnetic field to extreme levels. Not every collapsing stellar core meets those requirements. Most are born with strong but not extraordinary fields, becoming ordinary radio pulsars. Only a small percentage undergo the intense dynamo amplification that vaults their magnetic fields into the magnetar regime. The magnetar is the exception, not the rule. But it is a spectacular exception. Rarity does not mean insignificance. A single magnetar burst can release more energy in 1/10 of a second than the Sun emits in 100,000 years. The giant flare detected on March 5, 1979, the event that started this entire story, released as much energy in gamma rays as the Sun produces over roughly 1,000 years, all compressed into a fraction of a second, from a source 160,000 light-years away. And that event, as extraordinary as it was, would later be surpassed by an even more powerful eruption from a different magnetar. We will come back to that event. For now, what matters is this. A magnetar is a specific type of neutron star. It is not made of some exotic, unknown substance. It is not a theoretical construct from the fringes of speculative physics. It is a neutron star, born from the same kind of supernova that creates all neutron stars, composed of the same ultra-dense neutron-rich matter, held together by the same immense gravitational force. What sets it apart is its magnetic field. A field so powerful that it becomes the single most important feature of the object. A field that stores colossal quantities of energy within the star, reshapes the matter it threads through, controls the behavior of radiation and charged particles in the surrounding space, and drives some of the most violent electromagnetic events ever recorded by human instruments. The magnetar is, in the most literal physical sense, a dead star wrapped in the strongest magnetic field in nature. No fusion burns in its interior. No thermonuclear reactions sustain it. It is a remnant, the collapsed leftover of a star that exhausted its fuel and ended its life in a catastrophic explosion. But that remnant's magnetic field makes it one of the most dynamic and energetic objects in the known universe. The field stores energy in quantities that rival or exceed the total output of ordinary stars over thousands of years. And when that energy is released, the consequences are detectable across the galaxy and beyond. How that works, how a magnetic field can dominate the densest matter in existence, stress a rigid crystalline crust until it fractures, and unleash flares so powerful they disturb the upper atmosphere of a planet 50,000 light-years away. That is the story waiting ahead. Because the magnetar is not simply a neutron star with a strong magnet bolted onto its surface. The field is not a coating. It is not sitting on top of the matter like paint on a wall. It is threaded through every layer of the star, from the outermost crystalline crust, down through the superfluid interior and into the deepest, most uncertain regions of the core. It permeates the matter. It interacts with the matter. It competes with the matter. And in a magnetar, that competition between the densest material in the natural universe and the strongest fields in the natural universe creates physics that no laboratory on Earth can reproduce. Physics that pushes our best theories to the very edge of what they can describe. That competition is the heart of the magnetar story, and it is where we are going next. There is a temptation, when you first hear about magnetars, to imagine them as giant magnets. Enormous versions of the bar magnets you played with as a child, held together by magnetic force, the way a refrigerator magnet clings to a steel door. That image is wrong, and correcting it is essential to understanding what a magnetar actually is. A magnetar is not held together by its magnetic field. The magnetic field is not the skeleton of the object. It is not the glue. It is not the architecture. Gravity built this structure. Gravity and the behavior of matter crushed to densities beyond anything found on Earth. The magnetic field is a passenger, an occupant, an enormously powerful force threaded through every layer of the star. But if you could somehow switch off the magnetic field entirely, the neutron star would remain. Its mass would stay. Its density would stay. Its gravitational field, curving space-time so dramatically that light itself bends near the surface, would stay. The star would still be there, 20 kilometers across, containing more mass than the Sun, held together by gravity so strong that no known force in the universe except the internal pressure of ultra-dense matter can resist it. This distinction matters because it shapes everything that follows. The story of a magnetar is not the story of a magnet. It is the story of a competition. On one side is gravity, the force that crushed a stellar core down to a sphere the size of a city. Backing gravity up is the internal pressure of extraordinarily dense matter, the quantum mechanical resistance of neutrons packed so tightly that further compression would violate the fundamental rules of particle physics. These two forces, gravity pulling inward and pressure pushing outward, define the equilibrium that holds a neutron star in shape. They set the radius, the density, and the surface gravity, which is roughly 200 billion times stronger than Earth's. This equilibrium is described by a set of equations called the Tolman-Oppenheimer-Volkoff equations, the general relativistic version of the balance between gravity and pressure in a spherical object. Every neutron star, magnetar or not, obeys this balance. On the other side of the competition is the magnetic field. And while the field does not hold the star together, it is not irrelevant either. Far from it. A magnetar-strength magnetic field stores an almost inconceivable amount of energy within the star. It exerts forces on the matter it threads through. It can deform the crust. It can drive currents through the interior. It can rearrange itself over time, sometimes slowly and sometimes suddenly. And when its energy is released, the consequences are explosive. So the magnetar is not a giant magnet held together by magnetism. It is a gravitationally bound, pressure-supported sphere of ultra-dense matter, inside which the the strongest magnetic field in nature is trapped, coiled, and straining against the very structure that contains it. To understand this competition, you need to understand the structure of the neutron star itself. Because a neutron star is not a uniform ball of identical material. It has layers. Each layer has different physical properties, different composition, and a different relationship with the magnetic field. And the deeper you go, the more uncertain our understanding becomes. Start at the surface. The outermost layer of a neutron star is sometimes called the ocean or the atmosphere, depending on what the star's temperature and composition allow. For a young, hot magnetar, the surface may have a thin, gaseous atmosphere only centimeters thick, composed of light elements like hydrogen or helium. Below that, or sometimes directly at the surface if the atmosphere has been stripped away by intense radiation, you encounter the crust. The crust of a neutron star is one of the most remarkable materials in the known universe. It is a solid, a crystalline lattice of atomic nuclei arranged in a regular, repeating pattern, much like atoms are arranged in a crystal of iron or diamond here on Earth. But the conditions are vastly different. In the outermost parts of the crust, the nuclei are iron or similar heavy elements, the same kinds of nuclei you find at the core of ordinary matter. They are locked into a lattice by electrostatic forces between their positive charges, embedded in a sea of electrons that flow freely between them. The density at the top of the crust is roughly 1,000,000 times the density of water, already extreme by any terrestrial standard. As you descend deeper into the crust, density and pressure increase rapidly, and something remarkable happens. The nuclei become more and more neutron-rich. Under normal conditions on Earth, a nucleus with too many neutrons is unstable. It will undergo radioactive decay, emitting particles to reach a more balanced configuration. But inside the crust of a neutron star, the surrounding pressure is so extreme that these normally unstable nuclei are forced into stability. The pressure prevents them from decaying. They are squeezed into existence. Nuclei that could never survive for even a fraction of a second in any laboratory on Earth persist indefinitely inside the neutron star crust, held in place by the crushing weight of everything above them. Go deeper still, and you reach a layer called the neutron drip line. Here, roughly 600 meters below the surface, the density reaches a point where neutrons begin to leak out of the nuclei entirely. They drip free, forming a gas and eventually a fluid of unbound neutrons that fills the spaces between the lattice nuclei. Below the neutron drip line, you have a bizarre composite material, a crystalline lattice of neutron-bloated nuclei sitting in a bath of free-flowing neutrons, all permeated by a relativistic sea of electrons. Nothing remotely like this exists anywhere else in the observable universe except inside neutron stars. The total thickness of the crust is only about 1 to 2 kilometers, depending on the star's mass and the specifics of the equation of state, which describes how matter behaves at these extreme densities. That equation of state is one of the great open questions in nuclear physics. We know the general behavior, but the precise details, especially at the highest densities, are still debated. The crust, despite being thin compared to the star's total radius, plays a disproportionately important role in the Magnetar story. Because the crust is rigid. It is a solid. It has mechanical strength. It can bear stress up to a point. And that point is where things get violent. Below the crust lies the outer core, and this is where the bulk of the neutron star's mass resides. The outer core is a fluid, not a crystalline solid like the crust, but a liquid. However, it is not an ordinary liquid. The neutrons in the outer core, freed from nuclei entirely at these depths, form what physicists call a superfluid. A superfluid is a state of matter with effectively zero viscosity. It flows without friction. It can sustain currents that circulate indefinitely without slowing down. If you set a superfluid spinning, it would keep spinning forever unless something actively disturbed it. Superfluidity arises from quantum mechanics. At the extreme densities of the neutron star core, neutrons pair up through an attractive interaction and form what are called Cooper pairs, named after the physicist Leon Cooper. These paired neutrons behave collectively as a single quantum state, a condensate that flows without dissipation. This is the same basic physics behind superconductivity in metals on Earth, where electrons pair up and carry current without resistance. But here it happens with neutrons, at densities 100 trillion times greater than anything achievable in a laboratory. The protons in the outer core, a minority population alongside the overwhelming neutron majority, are also believed to form Cooper pairs. But protons carry electric charge, unlike neutrons. When charged particles pair up into a condensate, the result is not superfluidity, but superconductivity. The proton component of the outer core is thought to be a superconductor. This has direct consequences for the magnetic field. In an ordinary superconductor, magnetic fields are expelled from the interior through the Meissner effect. The superconductor pushes the field out, refusing to let magnetic flux penetrate its bulk. But in a neutron star, the situation is more complex. The proton superconductor is likely what physicists call a type II superconductor. In a type II superconductor, the magnetic field is not expelled entirely. Instead, it is confined into thin bundles called flux tubes, discrete filaments of magnetic field that thread through the superconducting material. Each flux tube carries a specific, quantized amount of magnetic flux. Picture this. In the outer core of a magnetar, the magnetic field does not spread out smoothly like it does in empty space. Instead, it is organized into an immense number of individual flux tubes, each incredibly thin, each carrying a tiny quantum of magnetic flux, each threading through a superconducting proton fluid embedded in a superfluid neutron background. The total field strength comes from the combined contribution of all these flux tubes packed together. The more densely they are packed, the stronger the effective magnetic field. In a magnetar, these flux tubes are packed extraordinarily tightly, and they are anchored to the superconducting fluid in ways that make them difficult to move or rearrange. Each flux tube is almost inconceivably thin. The diameter of a single flux tube in a neutron star core is estimated to be on the order of 10 to the minus 12 centimeters, far smaller than an individual atom, and yet each one is a real, distinct structure. A filament of magnetic field surrounded by circulating superconducting currents that screen the field from the surrounding material. The superconducting protons flow in tiny rings around each tube, creating current loops that confine the magnetic flux to the interior of the filament and prevent it from leaking outward into the surrounding superconductor. The total number of flux tubes threading through the core of a magnetar is enormous, potentially reaching 10 to the 34th or more. Millions of trillions of individual magnetic filaments, each one pinned in place by its interaction with the dense nuclear matter surrounding it. This pinning is not a minor detail. It is one of the reasons magnetars can sustain their extraordinary fields for thousands of years, rather than losing them in centuries or decades. Moving a flux tube requires overcoming the pinning force, which demands energy. The stronger the pinning, the more resistant the core field is to rearrangement and decay. The core becomes a magnetic vault, holding its flux in place long after the crustal field has evolved and partially dissipated. This is why the relationship between the crustal field and the core field is so important and so difficult to model. The crust evolves on one timescale, the core on another, and the boundary between them mediates a slow, complicated exchange of magnetic energy that governs the magnetar's long-term behavior and its observable properties across centuries and millennia. This has consequences for how the magnetic field evolves over time. In ordinary conducting matter, a magnetic field will gradually decay as electrical currents sustaining it dissipate through resistance. The field dies away, converting its energy into heat. This process is called ohmic decay. In a neutron star crust, ohmic decay does occur, but it operates on timescales of thousands to millions of years, depending on the temperature, composition, and structure of the crust. There is another process at work in the crust as well, called Hall drift. Hall drift does not dissipate the magnetic field directly. Instead, it rearranges the field geometry, shifting magnetic flux from one configuration to another. You can think of it as the magnetic field slowly sliding and reorganizing within the crust, carried along by the currents flowing through the electron sea. Hall drift can cascade energy from large-scale smooth field patterns into smaller-scale, more tangled configurations, which then decay more rapidly through ohmic dissipation. The interplay between Hall drift and ohmic decay governs how the crustal magnetic field evolves over thousands and tens of thousands of years. In the superconducting core, the situation is different. The superconducting protons resist changes to the magnetic flux threading through them. Flux tubes are pinned in place by interactions with the surrounding matter. Moving a flux tube requires energy. This pinning stabilizes the core magnetic field on very long timescales, potentially millions of years. The core field evolves much more slowly than the crustal field. This means the magnetic field inside a magnetar is not a single static entity. Different layers host different field components that evolve on different timescales. The crust may rearrange its field relatively quickly, on timescales of thousands of years, while the core retains its field configuration much longer. The relationship between the crustal and core fields, how they connect, how they exchange energy, how changes in one region propagate into the other, is an area of active and ongoing research. It is not fully understood. Now let us talk about the energy stored in this field, because that is where the magnetar's extraordinary violence comes from. A magnetic field contains energy. This is true of any magnetic field, from the feeble field of a refrigerator magnet to the field of the sun. The energy density of a magnetic field, the amount of energy stored per unit volume, is proportional to the square of the field strength. Double the field strength and you quadruple the energy density. Increase the field by a factor of 1,000 and you increase the energy density by a factor of 1,000,000. This scaling is crucial for magnetars. A magnetar's surface field is roughly 1,000 times stronger than that of an ordinary neutron star. That means the energy density in the field near the surface is about 1,000,000 times greater. And a magnetar is not small. It is 20 kilometers across, with a volume on the order of a few thousand cubic kilometers. When you integrate the energy density over that volume, accounting for how the field varies with depth and position, the total magnetic energy stored inside a magnetar is staggering. Estimates suggest it can reach roughly 10 to the 40 joules for the most strongly magnetized objects. To put that number in perspective, the Sun radiates about 3.8 times 10 to the 26 joules every second. At that rate, it would take the Sun hundreds of thousands of years of continuous output to radiate as much total energy as a magnetar stores in its magnetic field. Hundreds of thousands of years of sunlight locked inside a sphere 20 kilometers across, stored not as heat or nuclear fuel, but as pure magnetic energy. But here is something even more remarkable. The field we measure at the surface of a magnetar may not represent the full strength of the field inside. There is strong theoretical evidence that the internal magnetic field, particularly the toroidal component, coiled around the star's interior like a spring wound inside a donut, can be significantly stronger than the poloidal component visible at the surface. The poloidal field is the one that extends outward from the star, the one we can measure through its effects on spin-down and radiation. But the toroidal field is confined inside the star. It does not poke out through the surface. It wraps around the interior, hidden from direct external observation. Theoretical models and numerical simulations suggest the interior toroidal field in some magnetars could be several times or even 10 times stronger than the surface poloidal field. If the surface field is 1 quadrillion Gauss, the interior field could conceivably reach 10 quadrillion Gauss in localized regions. This interior field dominates the energy budget. Because the toroidal component fills a large volume of the star's interior, and because energy density scales with the square of field strength, even a modest increase in the interior field strength translates into a major increase in the total stored energy. The magnetar is like a container under enormous internal pressure. The energy is locked inside, stored in the configuration of the magnetic field threading through dense matter, and the rigid crust acts as the container wall, the shell that holds it all in. And this is where the competition becomes critical. The crust is strong. Neutron star crust material is the strongest known material in the universe, with a breaking strain estimated to be roughly 1/10. That means you can deform it by up to about 10% of its original shape before it fractures. For comparison, steel breaks at a strain of roughly a fraction of 1%. Neutron star crust is vastly stronger than any material on Earth. But strong is not infinite. The crust has limits, and the magnetic field is constantly testing those limits. As the magnetic field evolves through Hall drift and OH-Mc decay, it shifts and rearranges within the crust. As it does so, it exerts forces on the crustal lattice. The magnetic field pushes and pulls on the charged particles in the crust, particularly the electrons, and through them exerts stress on the entire crystalline structure. When the field is smooth and slowly varying, these stresses are modest, and the crust accommodates them by deforming slightly, flexing without breaking. But when the field configuration becomes more complex, when Hall drift cascades energy into smaller scale tangles and knots, the stresses can concentrate. Magnetic pressure builds in localized regions of the crust. The crust strains, it bends, it stores elastic energy like a spring being slowly compressed. If the magnetic stress exceeds the crust's breaking strain, the crust fractures. This is a starquake. And when a magnetar's crust breaks, the consequences are not subtle. The fracture allows a sudden rearrangement of the magnetic field, releasing the energy that was stored in the stressed configuration. The energy that was being held in check by the crust's mechanical strength is suddenly free. It pours out, driving violent high-energy emission. We will explore the details of these fractures and the flares they produce shortly. For now, the essential point is that the rigid crust acts as a bottleneck, a dam holding back the magnetic energy. The field pushes, the crust resists. And when the crust finally gives way, the result is one of the most energetic electromagnetic events in the universe. There is another layer we have not yet discussed, and it is the most uncertain of all. Below the outer core, at densities exceeding roughly 5 to 10 times the density of normal nuclear matter, lies the inner core. This is the deepest, densest region of the neutron star, and we genuinely do not know what matter looks like there. Our understanding of nuclear physics becomes increasingly uncertain at these densities because we cannot reproduce them in any experiment on Earth. Particle accelerators, like the Large Hadron Collider, collide particles at enormous energies, but they create hot, fleeting states of matter. The inner core of a neutron star is cold by nuclear physics standards and incredibly dense, a regime that no accelerator can replicate. Several possibilities have been proposed for the composition of the inner core. One possibility is that it remains composed of neutrons and protons, just at higher density, with the same basic physics as the outer core, but compressed further. Another possibility is that new particles appear. At high enough densities, it may become energetically favorable for some neutrons to transform into heavier baryons, called hyperons, particles like the lambda, sigma, or cascade that contain strange quarks. Hyperons are unstable in ordinary conditions, decaying in tiny fractions of a second. But at the densities inside a neutron star's inner core, the surrounding pressure may stabilize them, just as the crust stabilizes otherwise unstable neutron-rich nuclei. If hyperons are present, they change the mechanical properties of the core, generally making the matter softer and more compressible, which in turn affects the star's maximum possible mass and radius. An even more exotic possibility is that at the very highest densities, the distinction between individual neutrons and protons breaks down entirely. In ordinary matter, quarks are confined inside protons and neutrons. They cannot exist freely. This confinement is a fundamental property of the strong nuclear force, but theoretical calculations suggest that at sufficiently extreme densities, confinement may cease. Quarks may become deconfined, flowing freely in a state called quark matter, or a quark-gluon plasma condensate. If this happens in the inner core, the deepest region of the neutron star would not contain neutrons at all. It would contain a soup of free, up, down, and strange quarks, a phase of matter that has never been directly observed in bulk anywhere in the universe. Yet another possibility involves pion or kaon condensates, states where certain mesons, particles normally seen only as fleeting intermediaries in nuclear reactions, form a stable collective state inside the dense matter. Each of these possibilities leads to different predictions for the star's internal structure, its mass-radius relationship, its cooling behavior, and, critically, its interaction with the magnetic field. Why does the inner core composition matter for the magnetar story? Because the magnetic field threads through the entire star, including the inner core, and how that field behaves depends entirely on the properties of the matter it is embedded in. If the inner core is superconducting, it will confine the field into flux tubes and resist changes. If the inner core contains deconfined quark matter, the magnetic properties could be entirely different. Quark matter may be a color superconductor, a state in which quarks pair up in ways that have their own exotic magnetic behavior, potentially allowing different types of flux tubes or different rates of field evolution. The inner core's composition directly affects how much energy the magnetic field can store, how quickly that energy can be released, and what observational signatures the magnetar produces. And we simply do not know the answer. This is one of the honest uncertainties in magnetar physics, and in neutron star physics more broadly. The inner core remains a frontier. Different theoretical models make different predictions, and astronomers are working to test those predictions through increasingly precise observations of neutron star masses, radii, cooling rates, and oscillation modes. Every new measurement constrains the possibilities, narrowing the range of viable models. But the question is not yet settled. What we can say with confidence is this: a magnetar is a neutron star with a layered structure, a thin, rigid, crystalline crust over a thick, superfluid, superconducting outer core, over an uncertain, possibly exotic inner core. Threading through all these layers is a magnetic field of extraordinary strength. That field is not uniform. It has a complex geometry, with pole-oidal components that extend beyond the surface and toroidal components coiled deep inside. The field stores energy measured in quantities that rival thousands of years of solar output. It evolves over time through ohmic decay and Hall drift, slowly rearranging itself within the crust and interacting with the superconducting flux tubes of the core. As it evolves, it exerts mechanical stress on the rigid crust. The crust deforms, absorbing that stress elastically until the stress exceeds what the lattice can bear, and then the crust breaks. The gravitational field holds the star together. The pressure of dense matter supports it against collapse. The magnetic field does not maintain the structure, but it fills the structure with energy, pushes against the structure from within, and drives the most violent events the structure produces. The magnetar is a gravitational prison for the strongest magnetic field in the universe. And the walls of that prison, the rigid crystalline crust of the neutron star, are not infinitely strong. What happens when those walls crack? When the magnetic energy finally punches through, that is what comes next. The crust holds. That is the default state of a magnetar for most of its existence. The magnetic field pushes, the rigid crystalline lattice resists, and a tense equilibrium persists. Seconds pass, minutes, days, sometimes years. The field evolves slowly through Hall drift and ohmic decay, rearranging itself within the crust, shifting stress from one region to another. The lattice bends, absorbs the strain. It is the strongest known material in the universe, and for long stretches of time, that strength is enough. Then it is not enough. The stress concentrates. Hall drift cascades magnetic energy into smaller scale tangles, knotting the field lines into configurations that press harder on narrower regions of the crust. The elastic strain builds past the threshold, and the crust fractures. What happens next is extraordinarily fast. The fracture propagates through the crystalline lattice at a significant fraction of the speed of sound in that material, which, in neutron star crust, is a substantial fraction of the speed of light. The crack may span a region meters or even kilometers across on the surface. As the crust shifts, the magnetic field lines anchored to it are suddenly free to rearrange. A configuration that was being held in a stressed, high-energy state by the mechanical rigidity of the lattice is suddenly released. The field snaps into a lower energy configuration the way a compressed spring snaps back when you release the latch. And the energy difference between the old configuration and the new one does not vanish. It has to go somewhere. In a magnetar, that energy goes into the space above the surface. The sudden reconfiguration of the magnetic field launches energy outward, driving violent magnetic reconnection in the magnetosphere. Magnetic reconnection is the process by which oppositely directed magnetic field lines are brought together, break, and rejoin in a new topology, releasing the energy that was stored in the original configuration. This process is familiar to solar physicists. It powers solar flares on the sun. But on a magnetar, the field is roughly 1 trillion times stronger than in a solar active region, and the energy released is correspondingly more extreme. The reconnection heats the magnetospheric plasma to extraordinary temperatures. Pairs of electrons and positrons are created directly from the intense energy in the field, a process allowed by quantum electrodynamics when enough energy is concentrated in a small region. Within fractions of a second, a fireball of electron-positron plasma and high-energy radiation forms above the fracture site, trapped by the magnetic field lines that arch from the star's surface. The fireball is luminous. It radiates in X-rays and gamma rays, and if the fracture is large enough, the burst of radiation can be detected by instruments orbiting Earth, tens of thousands of light-years away. This is the mechanism behind what astronomers call soft gamma repeater bursts. The bursts are soft because their energy spectrum peaks at lower energies than classical gamma-ray bursts, typically in the range of tens to hundreds of kiloelectron volts rather than millions. And they repeat because the process is not a one-time catastrophe. The magnetic field continues to evolve after each fracture. Stress rebuilds, new tangles form, new fractures occur. A single magnetar can produce dozens or hundreds of bursts over years and decades of observation. Some are small, barely detectable flickers. Others are powerful enough to saturate space-based detectors. The pattern is irregular and unpredictable. A magnetar may sit quietly for months, producing nothing. then erupt in a flurry of bursts over the course of days, then go silent again for another long interval. This sporadic, repeating behavior is what originally drew attention to these objects in the 1970s and 80s, before anyone understood what was producing it. But the ordinary soft gamma repeater bursts, as violent as they are, pale in comparison to the rarest and most extreme events magnetars can produce. These are the giant flares. Only 3 have been confirmed in the history of observation. The first was the March 5, 1979 event from SGRO 526-66, the event we discussed earlier that first alerted astronomers to the existence of something profoundly unusual. The second occurred on August 27, 1998, from a magnetar designated SGR 1900+14. That flare was powerful enough to ionize the upper layers of Earth's night-side atmosphere from a distance of roughly 20,000 light-years. But the third giant flare is the one that truly revealed what magnetars are capable of. On December 27, 2004, a magnetar called SGR 1806-20 erupted with the most powerful magnetic explosion ever recorded by human instruments. SGR 1806-20 is located roughly 50,000 light-years from Earth, on the far side of the Milky Way galaxy. It sits in a region crowded with stars and gas near the galactic center. At that distance, ordinary astronomical events would be difficult to detect against the background. But this event was not ordinary. The initial spike of the giant flare lasted roughly 0.2 of a second. In that fraction of a second, the magnetar released roughly several times 10 to the 39 joules of energy in gamma rays alone. That is more energy than the Sun radiates in roughly 250,000 years, compressed into a time interval shorter than the blink of an eye. For that brief instant, SGR 1806-20 was emitting more energy per second than any other object in the observable universe at that moment. It briefly outshone the entire Milky Way galaxy in gamma rays. From 50,000 light-years away, the burst was so intense that it saturated nearly every gamma ray and X-ray detector in orbit. Instruments aboard spacecraft, including Integral, the Resi Solar Observatory, and multiple other satellites recorded the event, though many had their readings driven off-scale by the sheer intensity. Think about what that means in practical terms. Every major gamma-ray and X-ray observatory in orbit at the time was designed to study the most violent events the universe produces. Gamma-ray bursts, the deaths of massive stars, collisions between neutron stars, matter spiraling into black holes. These instruments were built with dynamic ranges engineered to handle the most extreme signals astrophysics could throw at them. And this single event from one magnetar on the far side of the galaxy overwhelmed them. The detectors were not designed to be fragile. They were designed for extremes, and the December 2004 flare exceeded those extremes. The burst struck Earth's orbital neighborhood like a wall. Spacecraft that were not even pointed at the source registered the event. Instruments designed to look at the Sun recorded it. Particle detectors registered secondary effects. The gamma-ray flux at Earth's distance, 50,000 light-years from the source, was still intense enough to be scientifically useful. Now consider what that flux would have been closer to the source. At a distance of 1 light-year, the radiation would have been lethal to any unshielded biology. At a distance of a few astronomical units, roughly the scale of a planetary system, the flux would have been sufficient to severely damage the ozone layer of an Earth-like planet, flooding its surface with harmful ultraviolet radiation for years afterward. If a magnetar giant flare of this magnitude occurred from a magnetar only 10 light-years away, which is well within the distance to several nearby stars, the gamma rays would be absorbed in the upper atmosphere, but would trigger chemical reactions that destroy stratospheric ozone. The damaged ozone layer would then allow increased solar ultraviolet radiation to reach the surface for months or years, with real consequences for exposed biology. The magnetar itself would not burn you directly from 10 light-years away. but it would strip away part of the invisible shield that protects you from your own star. We are fortunate that no known magnetar sits that close. The December 2004 event was not just the most powerful magnetar flare ever recorded. As of the most recent catalogues, it remains the most luminous transient electromagnetic event of any kind ever detected from a source within our own galaxy. It exceeded the luminosity of every observed galactic supernova remnant, every known X-ray binary outburst, every recorded solar flare by orders of magnitude. For 0.2 of a second, a dead star 20 kilometers across, producing no fusion energy whatsoever, outperformed the entire energy output of hundreds of billions of living stars combined. And it did so using nothing but the energy stored in its magnetic field. The effects reached Earth directly. The gamma rays travelled 50,000 light-years across the galaxy and struck Earth's upper atmosphere. Despite the enormous distance, the burst deposited enough energy in the ionosphere to measurably alter its electrical properties. The ionosphere is the layer of the atmosphere between roughly 60 and 1,000 kilometers altitude, where solar ultraviolet radiation strips electrons from atoms, creating a conducting layer that reflects certain radio waves. The December 2004 giant flare ionized the upper atmosphere further than normal, temporarily changing the way radio waves propagated around the planet. Instruments on the ground detected the disturbance. A magnetic event on a dead star halfway across the galaxy physically disturbed the atmosphere of Earth. That is how powerful a magnetar giant flare is. Following the initial spike, the December 2004 flare produced an oscillating tail of emission that lasted several minutes. This tail pulsated with the magnetar's rotation period of about 7.5 seconds, confirming that the source was a rotating neutron star. But embedded in that pulsating tail were additional frequencies. Researchers analyzing the data discovered quasi-periodic oscillations at frequencies of roughly 18, 26, 30, 92, 150, 625, and 1840 Hz. These oscillations were not random noise. They matched theoretical predictions for the vibrational modes of a neutron star, the seismic oscillations of the star's crust and core ringing like a bell after being struck. This was stunning. For the first time, astronomers were detecting the equivalent of seismic waves on the surface of a neutron star. Just as geologists on Earth study earthquakes to learn about the planet's internal structure, the layers of rock and metal and liquid beneath the surface, astrophysicists could use these quasi-periodic oscillations to probe the internal structure of the neutron star itself. The principle is almost identical to what geologists do on Earth. When an earthquake strikes, seismic waves propagate through the planet's interior. Different types of waves, pressure waves and shear waves, travel at different speeds depending on the density and rigidity of the material they pass through. By recording how these waves arrive at seismometers scattered across the globe, geologists have mapped the internal structure of Earth in extraordinary detail. They identified the boundary between the solid mantle and the liquid outer core. They discovered the solid inner core. They mapped the thickness of the crust under continents and oceans. All of this without ever drilling deeper than a few kilometers. The interior of the Earth was revealed by listening to the planet vibrate. Magnetar seismology works on the same fundamental idea, but under vastly more extreme conditions. The material is not rock and iron. It is neutron-rich nuclear matter at densities exceeding 100 trillion times the density of water. The restoring forces are not the elasticity of minerals, but the shear modulus of a crystalline lattice made of neutron-bloated nuclei and the pressure of superfluid neutrons beneath it. The oscillation frequencies are not fractions of a hertz, as in terrestrial earthquakes, but tens, hundreds, and even thousands of hertz. Audible frequencies, if you could somehow convert them into sound. The magnetar, after a giant flare fractures its crust, rings at frequencies you could hear if your ear were somehow capable of detecting oscillations in X-ray intensity rather than oscillations in air pressure. A neutron star, vibrating at roughly 625 Hz, would sound like a note close to the E-flat, about 1 octave above middle C on a piano. The densest object short of a black hole, ringing like a musical instrument. This is not poetry, it is data. The frequencies were measured from real photon counts recorded by real instruments in orbit, and each frequency carries quantitative information about the star's structure. A shear mode confined to the crust oscillates at a frequency that depends on the crust's thickness, its shear modulus, and the density profile through the crystalline lattice. A mode that penetrates into the fluid core is sensitive to the superfluid density and the coupling between the crust and the core. By comparing the observed frequencies with theoretical predictions from different neutron star models, researchers can rule out models that predict the wrong frequencies and favor models that match the data. Different oscillation frequencies correspond to different vibrational modes. Some are surface shear waves, ripples propagating through the crystalline crust. Others are deeper modes, vibrations that penetrate into the core and are sensitive to the properties of the dense matter there. By measuring which frequencies are excited and at what amplitudes, researchers can test models of the neutron star's interior, constraining the equation of state, the thickness and composition of the crust, and the properties of the superfluid and superconducting core. This is an active and ongoing area of research. The quasi-periodic oscillations detected in the December 2004 flare, and to a lesser extent in the other two giant flares, provide some of the most direct observational constraints we have on the internal structure of neutron stars. They are not easy to interpret. The theoretical models involve complex coupling between the magnetic field, the elastic crust, and the fluid core, and different assumptions about these couplings lead to different predictions. But the data exist. The star rang, and we heard it. And, with better models and potentially future detections of giant flares, these oscillations may eventually tell us what the inside of a neutron star looks like, with much greater precision than we currently possess. But giant flares are not the only way magnetars announce themselves. Between bursts, magnetars glow. They emit a steady, persistent luminosity in X-rays, typically in the range of 10 to the 26 to 10 to the 29 joules per second. This is far brighter than what ordinary rotation-powered pulsars produce at comparable ages. An ordinary pulsar derives its X-ray luminosity primarily from the kinetic energy of its rotation. As the pulsar spins and its rotating magnetic field generates electromagnetic radiation, it gradually slows down, converting rotational energy into emitted power. But magnetars spin relatively slowly, with rotation periods of roughly 2 to 12 seconds. They do not have enough rotational energy to account for their observed X-ray brightness. The luminosity exceeds what the spin-down energy can supply, in some cases by factors of 10 or 100. The explanation in the magnetar model is that the persistent X-ray emission is powered by the decay of the magnetic field itself. As the field evolves through OH-MIC decay and Hall drift in the crust, and as flux tubes migrate and interact in the core, magnetic energy is gradually converted into heat. This heat diffuses through the star and radiates from the surface as thermal X-rays. The magnetar is glowing because its magnetic field is slowly dying, releasing the enormous reservoir of energy stored in the field configuration over thousands and tens of thousands of years. This process is called magnetically powered emission, and it distinguishes magnetars from every other class of neutron star. The energy source is not rotation. It is not accretion of matter from a companion star. It is the magnetic field itself, draining its energy into the star's thermal budget and producing a persistent glow visible across the galaxy to X-ray telescopes in orbit. The the rate of this energy release is not constant. As the field evolves and tangles develop through Hall drift, localized regions of the crust may heat up more intensely, creating hotspots on the surface that contribute disproportionately to the observed X-ray emission. These hotspots can shift and change as the field configuration evolves, causing the persistent luminosity to vary on timescales of months to years. Some magnetars show gradual changes in their pulse profiles over time, consistent with evolving surface hotspot patterns. The connection between internal field evolution and observable surface emission is a rich area of theoretical modeling, tying the deep interior physics of the star to what telescopes actually measure. Now let us step away from the surface and look at what the magnetic field does to the space around the magnetar. Because the field does not stop at the surface, it extends outward into the vacuum, creating a magnetosphere, a vast, structured environment of magnetic field lines, charged particles, and radiation that surrounds the star for thousands of kilometers. In the magnetosphere of a magnetar, the magnetic field is the dominant force governing everything. Near the surface, the field strength is on the order of 1 quadrillion Gauss. Even at a distance of a few hundred kilometers, where the field has dropped significantly from its surface value, it remains stronger than anything achievable in a terrestrial laboratory. The field lines arch outward from the magnetic poles, curve through space, and return to the surface at the opposite pole, forming closed loops. Along these loops, charged particles spiral tightly, guided and confined by the magnetic force. The particles cannot move freely across the field lines. They can only move along them, spiraling in tight helical paths. The magnetic field acts as a set of rails, channeling the motion of every charged particle in the magnetosphere. This confinement has consequences for how radiation behaves. In a strong magnetic field, the way photons interact with charged particles changes dramatically. One of the key processes is Compton scattering, the interaction in which a photon bounces off an electron, exchanging energy and changing direction. In a weak magnetic field, or no field at all, Compton scattering behaves in a well-understood way described by standard quantum electrodynamics. But in a magnetar strength field, the electrons are confined to the lowest Landau levels, quantized energy states corresponding to the cyclotron motion of the electron around the magnetic field line. The scattering cross-section, the probability that a photon will interact with an electron, becomes strongly dependent on the photon's energy and polarization relative to the field direction. Photons polarized parallel to the field interact very differently than photons polarized perpendicular to it. This creates a natural polarization filter in the magnetosphere. Radiation escaping from the surface of a magnetar passes through a region where the scattering depends on polarization, and the radiation that reaches distant observers carries an imprint of the magnetic field geometry. This magnetic filtering of radiation is not a subtle theoretical effect. It produces measurable differences in the X-ray spectra and pulse profiles observed from magnetars. As the magnetar rotates, different regions of its magnetosphere sweep across our line of sight. Each region has a slightly different field geometry, a different orientation of field lines relative to the photons passing through. The scattering conditions change accordingly. Photons that escape easily through one region of the magnetosphere may be heavily scattered in another. The result is that the X-ray pulse profile, the pattern of brightness variation we observe as the magnetar spins, encodes information about the three-dimensional magnetic field structure. By modeling how the pulse profile changes with energy and comparing those models to observations, astronomers can reconstruct aspects of the field geometry that would otherwise be completely hidden from view. The Compton scattering process itself also produces a distinct spectral feature. When a photon has exactly the right energy to resonate with the cyclotron frequency of an electron spiraling around a field line, the scattering probability spikes dramatically. This creates what is called a cyclotron resonance feature, an absorption or emission line in the X-ray spectrum at an energy determined by the local magnetic field strength. In ordinary X-ray pulsars, with fields of roughly 1 trillion Gauss, cyclotron lines appear at energies of tens of kilo-electron volts and have been observed in dozens of sources. In magnetars, where the field is 1,000 times stronger, the fundamental electron cyclotron energy shifts upward into the mega-electron volt range, far above the thermal X-ray peak where most of the detectable emission lies. The feature is effectively pushed out of the observable spectrum. There is simply not enough photon flux at those extreme energies for current instruments to detect the cyclotron signature. Proton-cyclotron features, which occur at roughly 1,800 times lower energy than electron features due to the proton's greater mass, fall in the kilo-electron volt range for magnetar strength fields and are therefore more promising targets. Several candidate proton-cyclotron absorption features have been tentatively identified in magnetar X-ray spectra, though definitive confirmation remains elusive because the strong magnetic field gradient across the emission region smears the feature and complicates interpretation. But the search for cyclotron features in magnetar spectra remains an active observational pursuit because a confirmed detection would provide a direct, model-independent measurement of the magnetic field strength at the scattering location. No inference from spin-down rates. No dependence on theoretical models of field geometry, just a spectral line whose energy tells you the field strength directly. Even more remarkable is a process called photon splitting. In empty space, far from any strong field, photons do not interact with each other. Light passes through light. Two beams of light can cross without either one being affected. But in a magnetic field approaching the quantum electrodynamic critical value, roughly 4.4 times 10 to the 13 Gauss, the vacuum itself becomes a medium with non-linear electromagnetic properties. Photons can interact with the virtual electron-positron pairs that constantly fluctuate in and out of existence in the vacuum, mediated by the intense magnetic field. One consequence is that a single photon can split into two lower energy photons, a process forbidden in empty space but permitted in a super strong magnetic field. This process is not merely theoretical. It is a firm prediction of quantum electrodynamics, calculable from first principles, and the magnetar environment is one of the very few places in the universe where the field strengths are high enough for it to occur at an appreciable rate. Photon splitting has observational consequences. It tends to suppress high-energy photons in the radiation escaping from the magnetar surface, because high-energy photons split into pairs of lower-energy photons before they can travel far. It also affects the polarization of the escaping radiation, because the splitting rates differ depending on the photon's polarization relative to the field direction. By measuring the spectrum and polarization of a magnetar's persistent X-ray emission, astronomers can test the predictions of quantum electrodynamics in a regime completely inaccessible to laboratory experiments. The magnetar becomes a natural laboratory for fundamental physics, testing theories about the interaction of light and magnetic fields at field strengths roughly 1 billion times greater than anything humans can produce. The magnetosphere is also where the connection between the star and the broader universe plays out. As the magnetar rotates, its magnetic field sweeps through the surrounding space. Charged particles in the magnetosphere are accelerated by the rotating field, gaining energy and producing radiation across the electromagnetic spectrum. This is broadly similar to what happens around ordinary pulsars, where the rotating magnetic field drives particle acceleration and powers the pulsed emission we detect as radio pulses. But in a magnetar, the field is so much stronger that the processes are amplified to an entirely different scale. The energy available for particle acceleration is vastly greater. The radiation produced can extend from radio wavelengths all the way up to hard X-rays and soft gamma rays. Some magnetars have been detected as radio pulsars, but with unusual properties. Their radio pulses are highly variable, changing in shape and intensity from one rotation to the next, sometimes disappearing entirely and then reappearing. The radio emission from magnetars appears to be linked to their magnetic activity. Some magnetars have been observed to turn on as radio sources following a burst or outburst, then gradually fade in radio brightness over weeks or months. This suggests that the radio emission mechanism is connected to the transient rearrangement of the magnetic field, rather than the steady rotational process that drives ordinary pulsar emission. The magnetosphere extends far from the star, but its influence is not unlimited. At a distance called the light cylinder radius, defined as the distance at which the magnetic field lines would have to co-rotate with the star at the speed of light, the closed magnetosphere ends. Beyond the light cylinder, field lines cannot remain closed. They open up, and any plasma attached to them is flung outward into space, carrying energy and magnetic flux away from the star in a magnetar wind. This wind contributes to the spin down of the magnetar, extracting rotational energy and carrying it away. For ordinary pulsars, the wind is the primary mechanism of energy loss. For magnetars, the magnetic field decay provides an additional, often dominant energy source beyond what the wind removes. Inside the light cylinder, the closed magnetosphere forms a complex, dynamic environment. The field lines are not static. They are stressed by the rotation of the star, by the currents flowing along them, by the evolving field configuration at the surface, and by the weight of the trapped plasma. In the aftermath of a burst or flare, the magnetosphere may be filled with hot electron-positron plasma, slowly cooling and radiating over seconds to minutes. During giant flares, the trapped fireball can contain enormous amounts of energy, radiating intensely as it gradually leaks out along the field lines. The pulsating tail of the December 2004 giant flare was produced by exactly this mechanism. A massive fireball of plasma and radiation trapped in the magnetosphere, modulated by the star's rotation as the fireball presented different aspects to the observer. The environment within a few hundred kilometers of a magnetar surface is one of the most extreme places in the known universe. The gravitational field warps space-time noticeably. The magnetic field distorts atoms, alters the vacuum, splits photons, and confines charged particles to tight spiral paths along field lines. The density of the surface material exceeds anything else in nature, short of a black hole singularity. The temperature of the surface can reach millions of degrees during active periods, and through all of this, the star persists. It does not fly apart, it does not collapse further, unless its mass is pushed above the maximum that neutron star matter can support, at which point it would collapse into a black hole. But below that limit, the magnetar endures. Gravity holds, pressure resists, and the magnetic field continues its slow, violent confrontation with the matter that contains it. The magnetar's active phase, the period during which its magnetic field is strong enough to power detectable bursts and persistent X-ray emission, does not last forever. Estimates suggest it lasts roughly 10,000 years. After that, the field has decayed sufficiently that the energy reservoir is depleted below the level needed to fracture the crust or sustain luminous emission. The object does not vanish. It is still a neutron star. It still has mass, gravity, density, rotation, but it becomes magnetically quiet, indistinguishable from an old, slowly rotating, dim neutron star. It fades into the vast population of dead, silent neutron stars scattered throughout the galaxy. The magnetar phase is brief on astronomical timescales, a flash of magnetic violence in a star's long afterlife, and then silence. But during those 10,000 years, a magnetar does more than just flare and glow. It does something no laboratory on Earth can replicate. It generates conditions where the most extreme predictions of quantum electrodynamics, general relativity, and nuclear physics all become relevant simultaneously. It tests our theories at their limits. And what those tests reveal about the fundamental nature of matter, fields, and the vacuum itself is where we are going to end this story. There is a question that sits beneath everything we have discussed so far. A question that is easy to forget when you are captivated by the violence of giant flares and the strangeness of photon splitting and the impossible density of neutron star matter. The question is this: why does any of this matter to us? We will never visit a magnetar. We will never build one. We will never hold magnetar strength fields in a laboratory. These objects exist tens of thousands of light years away, visible only through specialized telescopes in orbit, producing radiation that our atmosphere mercifully absorbs before it reaches the ground. So why should anyone care? The answer is that magnetars give us something we cannot get any other way. They are natural laboratories for physics at the absolute extreme, creating conditions where our best theories are pushed to their breaking points. What we learn does not stay confined to astrophysics. It feeds back into our fundamental understanding of matter, fields, energy, and the vacuum itself. Consider what the magnetic field near a magnetar surface does to the vacuum. In everyday experience, the vacuum of empty space is featureless. It has no structure. Light passes through it without encountering anything. All directions are equivalent. All polarizations of light travel at the same speed. The vacuum is, to our senses, and to most of our instruments, nothing. But quantum electrodynamics, the theory describing how light and charged particles interact at the quantum level, tells a different story. According to QED, the vacuum is not truly empty. It is filled with a constant seething of virtual particles. Electron-positron pairs flicker into existence and annihilate again in inconceivably short intervals, borrowing energy from the vacuum in amounts permitted by the Heisenberg uncertainty principle. Under normal conditions, these fluctuations have no visible effect. But in a sufficiently strong magnetic field, the virtual electron-positron pairs are affected. The magnetic field polarizes them, stretching and aligning the virtual pairs along the field direction. This polarization gives the vacuum itself an optical structure. It becomes birefringent, meaning it bends light differently depending on the polarization of the photon relative to the magnetic field direction. A photon polarized parallel to the field experiences a slightly different refractive index than a photon polarized perpendicular to it. The two polarizations travel through the magnetized vacuum at very slightly different speeds and along very slightly different paths. This is called vacuum birefringence, and it is one of the most remarkable predictions of QED. It was predicted theoretically in the 1930s and 40s, but for decades it seemed untestable because the effect is unmeasurably small at field strengths achievable in any laboratory. The strongest sustained magnetic field humans have produced is about 45 Tesla. The field strength at which vacuum birefringence becomes significant is the Schwing-Ur critical field, named after physicist Julian Schwing-Ur, approximately 4.4 times 10 to the 9th Tesla. That is roughly 100 million times stronger than our best laboratory magnets. There is no foreseeable technology that could bridge that gap. No magnet, no pulsed field device, no superconducting coil will ever reach the Schwing-Ur limit in a controlled experiment on Earth. But magnetars reach it. The surface fields of the strongest known magnetars approach or even exceed the Schwing-Ur critical value. In the space immediately above these stars, the vacuum is measurably birefringent. The empty space around a magnetar behaves like a crystal, bending light differently depending on its polarization, and this effect, predicted on paper nearly a century ago, can, in principle, be detected by measuring the polarization of X-rays coming from magnetar surfaces. In 2022, the Imaging X-ray Polarimetry Explorer, or IXPE, a joint mission between NASA and the Italian Space Agency, began making polarization measurements of X-ray sources across the sky. IXPE is the first space observatory specifically designed to measure the polarization of cosmic X-rays with high precision. Among its targets are magnetars and other strongly magnetized neutron stars. Although definitive confirmation of vacuum birefringence from magnetar observations is still being refined and debated as of the most recent published results, earlier observations of an isolated neutron star designated RxJ 1856.5-3754 using visible light polarimetry with the Very Large Telescope in Chile had already found polarization signals consistent with vacuum birefringence predictions. The measurements are at the edge of current capability, and the interpretation involves careful modeling of the neutron star atmosphere and magnetic field geometry. But the data are heading in the direction that QED predicts. Nature appears to behave exactly as the theory says it should, even in regimes we thought we would never be able to test. This is why magnetars matter beyond astrophysics. They are testing QED in a domain that no particle accelerator, no laser facility, no condensed matter laboratory can access. If the observations confirm vacuum birefringence precisely, they validate QED at field strengths 100 million times beyond our experimental reach. If they reveal deviations from the predictions, they would signal the presence of new physics beyond QED, potentially pointing toward unknown particles or interactions that only become relevant at extreme field strengths. Either outcome is profoundly valuable. There are other QED effects relevant to magnetar strength fields. We discussed photon splitting earlier. Another is magnetic pair creation, the process by which a single photon traveling through a sufficiently strong magnetic field spontaneously converts into an electron-positron pair without needing to collide with anything. In empty space without a magnetic field, a photon cannot do this. Energy and momentum conservation forbid it. But the magnetic field can absorb the necessary recoil momentum, acting as a silent partner in the interaction. Above a threshold photon energy that depends on the field strength, magnetic pair creation becomes possible and eventually dominant. In the strongest magnetar fields, this process limits how energetic photons can be before they are absorbed and converted into pairs. It shapes the high-energy spectrum of magnetar emission in ways that are directly observable with gamma-ray telescopes. Each of these QED processes, vacuum birefringence, photon splitting, magnetic pair creation, resonant Compton scattering in quantized Landau levels, is calculable from first principles. The predictions are precise. The magnetar provides the laboratory, and the comparison between prediction and observation tells us whether our understanding of the quantum vacuum is correct. No other astrophysical source offers this combination of extreme field strength and observable electromagnetic signatures. Now let us turn to a different question. How are magnetars born? What determines whether a collapsing stellar core produces an ordinary neutron star with a trillion Gauss field, or a magnetar with a field 1,000 times stronger? This is one of the central open questions in magnetar physics, and while we have a leading theoretical framework, the details remain actively debated. The most widely accepted formation model is the dynamo hypothesis, proposed by Robert Duncan and Christopher Thompson in 1992, the same work that introduced the magnetar concept. Their argument centers on the first 10 to 30 seconds after the core collapse that creates the neutron star. During this brief interval, the proto-neutron star is extraordinarily hot, with internal temperatures exceeding 100 billion degrees. At these temperatures, the matter inside is not yet in its final, cold, dense state. It is a hot, rapidly convecting fluid of neutrons, protons, electrons, and neutrinos. Neutrinos, produced in enormous quantities during the collapse, are still trapped inside, slowly diffusing outward through the dense matter. Their diffusion drives vigorous convective motion, churning the interior like a pot of water heated violently from below. If the proto-neutron star is also rotating rapidly, with a spin period of a few milliseconds or less, the combination of rapid rotation and vigorous convection creates the conditions for a magnetic dynamo. A dynamo is a self-sustaining process in which the motion of an electrically conducting fluid amplifies a weak seed magnetic field into a much stronger one. The kinetic energy of the fluid motion is converted into magnetic energy. Dynamos operate inside the Earth, where the churning of molten iron in the outer core sustains our planet's magnetic field. They operate inside the Sun, where convective motions in the solar interior drive the 11-year solar magnetic cycle. And Duncan and Thomson showed that they could operate inside a newborn neutron star, but at incomparably greater intensity. The basic principle of a dynamo is elegant. Imagine a weak magnetic field line threading through a conducting fluid. If the fluid moves, it drags the field line with it because the field is frozen into the conducting material, unable to slip through it freely. Now imagine the fluid is not just moving, but churning, rotating differentially so that adjacent layers move at different speeds. The field line gets stretched. It gets wound around the rotation axis like thread on a spool. Each winding amplifies the field because stretching a field line increases the field strength along its length, the way stretching a rubber band increases its tension. Convective plumes, rising and sinking through the fluid, fold the stretched field lines over on themselves, creating new loops and tangles. Each fold doubles the complexity. Each stretch increases the intensity. The process feeds on itself. The stronger the field becomes, the more energy can be extracted from the fluid motion to amplify it further, until the magnetic energy grows large enough to push back on the fluid and resist further amplification. This saturation point, the balance between the kinetic energy of the convection and the magnetic energy of the amplified field, determines the final field strength. In the interior of a newborn neutron star, this process operates at an intensity beyond any other known dynamo in the universe. The fluid is not molten iron moving at centimeters per second as in Earth's core. It is nuclear density matter churning at thousands of kilometers per second, driven by neutrino-powered convection, releasing up to 10 to the 46 joules per second at its peak. The conductivity of the fluid is nearly perfect. The rotation rate is hundreds of revolutions per second. Every parameter that governs dynamo efficiency is pushed to its physical maximum simultaneously. The result is a field amplified to strengths that no other astrophysical process can produce. The key parameter is the initial rotation rate. If the proto-neutron star is spinning with a period of roughly 1 to 3 milliseconds, the convective dynamo can amplify the magnetic field to magnetar levels within seconds. The rotational energy available in a millisecond spinning neutron star is enormous, roughly 10 to the 45 joules or more, comparable to the kinetic energy of the supernova explosion itself. The dynamo taps this rotational energy, converting a fraction of it into magnetic energy. The amplification is exponential. Each convective turnover cycle winds and stretches the field lines, increasing the field strength. Within 10 to 20 seconds, before the star cools and the convection ceases, the field can reach 1 quadrillion Gauss or higher. After that, the convection stops, the star solidifies into its layered structure, and the amplified field is frozen in. The magnetar is born. But not every neutron star is born spinning fast enough. The initial rotation rate of the proto-neutron star depends on the rotation rate of the original stellar core before collapse, and on how angular momentum is redistributed during the collapse itself. Most stellar cores are probably not spinning rapidly enough to drive an efficient dynamo to magnetar strength fields. They produce ordinary neutron stars with trillion Gauss fields that are strong by any standard, but 1,000 times weaker than magnetar fields. These ordinary fields may result from simple magnetic flux conservation during collapse, the compression mechanism we discussed earlier, without any additional dynamo amplification. The fraction of neutron stars born as magnetars is estimated to be roughly 10%, though this number is uncertain. It depends on the distribution of initial rotation rates, which in turn depends on the details of stellar evolution, mass loss, binary interactions, and the physics of the collapse itself. These are all areas of active research. Some models suggest the fraction could be higher or lower. The observed number of active magnetars in the galaxy, roughly 30 confirmed, is consistent with a birth rate of a few per century if the active phase lasts about 10,000 years. This matches the rough supernova rate in the Milky Way, which is about 2 to 3 per century, if roughly 10% of those supernovae produce magnetars. There are alternative formation scenarios as well. Some researchers have proposed that magnetars could form through the merger of two white dwarf stars, compact stellar remnants that are far less dense than neutron stars. If two massive white dwarfs spiral together and merge, the resulting object could collapse into a neutron star. The violent, rapidly rotating merger remnant might drive a dynamo similar to the one proposed for core collapse supernovae, potentially creating a magnetar. This channel is more speculative and probably less common than the core collapse route, but it remains a theoretical possibility. Another proposal is that strong magnetic fields could be inherited rather than generated. Perhaps some massive stars already have unusually strong magnetic fields before they collapse. A small fraction of massive stars, roughly 7 to 10%, are observed to have strong surface magnetic fields of hundreds or thousands of Gauss. If such a star collapses and its field is amplified purely through flux conservation, the resulting neutron star might already have a field in the magnetar range without needing a dynamo at all. This fossil field hypothesis is debated. Some calculations suggest that flux conservation alone cannot produce magnetar strength fields from observed stellar fields without additional amplification. Others argue it might be sufficient in extreme cases. The honest summary is that we believe the dynamo mechanism is the most likely path to magnetar formation, but we do not have definitive proof. The formation event happens deep inside a collapsing star, hidden behind the opaque layers of the supernova explosion, inaccessible to direct observation. We infer the mechanism from the properties of the magnetars we observe and from theoretical models of the collapse process. Future observations, particularly of very young magnetars associated with supernova remnants, whose ages and energies can be independently estimated, may help constrain the formation mechanism further. We have established that the active phase of a magnetar, the period during which its magnetic field is strong enough to power detectable emission and violent flares, lasts roughly 10,000 years. After that, the field decays below the threshold needed to fracture the crust or sustain bright X-ray emission. But the field does not disappear instantly. It fades gradually, and during this decline, the magnetar transitions from a brilliant, bursting source into a quieter object, perhaps resembling an ordinary X-ray dim, isolated neutron star. Eventually, over hundreds of thousands or millions of years, the object becomes virtually undetectable, except through its gravitational effects or faint thermal emission as it slowly cools. The galaxy is likely populated with millions of dead magnetars, objects that once raged with the strongest fields in nature, but have long since fallen silent. There is a remarkable twist in the magnetar story that connects these objects to one of the biggest mysteries in modern astrophysics. Fast radio bursts, or FRBs, are brief, intensely luminous pulses of radio emission lasting only milliseconds, arriving from enormous distances, often from other galaxies, hundreds of millions or even billions of light-years away. They were first discovered in 2007, and since then, hundreds have been detected by radio telescopes around the world. Some repeat, producing multiple bursts from the same source over days or months. Others appear to burst once and never again. Their origin was one of the most hotly debated topics in astrophysics for over a decade. On April 28, 2020, a magnetar in our own galaxy, designated SGR 1935+2154, produced a radio burst so intense that it was detected by multiple instruments, including the Canadian Hydrogen Intensity Mapping Experiment, known as CHIME, and the Survey for Transient Astronomical Radio Emission 2, known as STARE-2. The burst had many of the hallmarks of a fast radio burst. It was brief, lasting only milliseconds. It was extraordinarily bright in radio wavelengths. And critically, it was accompanied by a simultaneous X-ray burst from the same magnetar, detected by space-based X-ray telescopes. This was the first time a fast radio burst-like event had been convincingly associated with a known astrophysical source. The detection was not a perfect match to the most luminous cosmological fast radio bursts, which are far more energetic than the April 2020 event. The galactic magnetar burst was roughly 1,000 times less luminous than the weakest extragalactic fast radio bursts detected at that time. But the gap is not insurmountable. If magnetars occasionally produce radio bursts spanning a wide range of energies, the most powerful events from magnetars in other galaxies could be luminous enough to match the observed fast radio burst population. The April 2020 detection established that magnetars can produce millisecond duration radio bursts with the right characteristics. Whether magnetars are the sole source of all fast radio bursts, or just one source among several, remains an open question. But the connection is no longer speculative. It is grounded in a direct, observed association between a known magnetar and a fast radio burst-like emission event. This connection has enormous implications. If most or all fast radio bursts originate from magnetars, then every fast radio burst detection is a probe of magnetar physics at cosmological distances. The properties of the bursts, their durations, spectra, polarization, repetition patterns, and energetics, all encode information about the magnetic fields and magnetospheric processes of neutron stars in galaxies far beyond our own. Fast radio bursts become tools for studying magnetars across the observable universe, not just the handful visible in our galaxy. And because fast radio bursts travel through intergalactic space before reaching us, their signals carry imprints of the material they passed through, making them useful for probing the distribution of matter between galaxies as well. A connection between magnetars and fast radio bursts links neutron star physics to cosmology in a way nobody anticipated when soft gamma repeaters were first detected in the 1970s. So where does all of this leave us? What do we know? What do we not know? And why does the distinction matter? We know that magnetars are neutron stars. They are composed of ultra-dense, neutron-rich matter held together by gravity, structured in layers of increasing density and decreasing certainty, from a crystalline crust through a superfluid and superconducting core to an inner region whose composition remains genuinely unknown. We know their magnetic fields are the strongest, persistent fields in the known universe, storing enormous quantities of energy that can be released through crustal fractures and magnetic reconnection, producing bursts and flares detectable across the galaxy. We know the field shapes the surrounding environment, confining charged particles, altering the behavior of radiation, and even modifying the optical properties of the vacuum through the predictions of quantum electrodynamics. We know the active magnetar phase lasts roughly 10,000 years, after which the field decays and the object fades. And we have strong evidence connecting magnetars to fast radio bursts, linking these extreme objects to one of the most active frontiers in observational astrophysics. What we do not know is equally important. We do not know exactly how magnetar strength fields are generated. The dynamo hypothesis is compelling, but it depends on initial conditions, the rotation rate and convective vigor of the proto-neutron star that we cannot directly observe. We do not know the detailed three-dimensional geometry of the magnetic field inside a magnetar. Is the toroidal component truly dominant over the poloidal component? How are the field lines configured in the deepest layers of the core? How does the field thread through the transition between the solid crust and the fluid interior? These questions have theoretical answers that depend on assumptions, and those assumptions have not been definitively tested. We do not know what the innermost core of a magnetar or any neutron star is made of. Neutrons and protons may persist to the center, or hyperons may appear, or quarks may become deconfined, forming a state of matter never directly observed. The composition of the inner core affects how the magnetic field behaves at the greatest depths, and until we understand the equation of state of ultra-dense matter with confidence, our models of magnetar interiors will remain incomplete. This uncertainty is not a failure. It is the frontier. It is where the next discoveries are waiting. We do not fully understand the triggering mechanism for giant flares. We know the crust fractures, but what determines when and where a fracture initiates? Why do most fractures produce modest bursts, while a tiny fraction produce giant flares releasing 10,000 times more energy? Is there a critical threshold in the stress pattern, a tipping point where a small fracture cascades into a catastrophic rearrangement of the entire global field? These questions connect magnetar physics to the broader science of catastrophic failure, the same mathematics that governs earthquakes, avalanches, and fractures in engineered materials, scaled up to conditions that no terrestrial material will ever experience. And we do not know whether magnetars are the sole source of fast radio bursts. The April 2020 detection showed that magnetars can produce such bursts, but the most luminous fast radio bursts from distant galaxies are far more energetic. Can ordinary magnetar activity account for those extreme events, or do they require something different? A younger magnetar, a more powerful flare, a fundamentally different mechanism. This question sits at the intersection of neutron star physics and cosmology, and answering it is one of the highest priorities in observational astrophysics today. These uncertainties are not embarrassments. They are the reason magnetars remain one of the most exciting objects in modern science. Each open question is an invitation to build better X-ray telescopes that can map magnetic field geometries through polarimetry, an invitation to detect gravitational waves from magnetar starquakes, carrying direct information about the crust and the density beneath it, an invitation to develop better theoretical models of ultra-dense matter, an invitation to detect more fast radio bursts and trace them back to their sources, building a statistical picture of whether magnetars account for all of them or only some. Every magnetar sitting quietly in the galaxy right now, glowing faintly in X-rays, occasionally fracturing its crust and hurling bursts of radiation into the void, is a laboratory performing experiments that human civilization cannot perform. It subjects matter to fields that are 1 billion times stronger than anything we can produce. It compresses material to densities that no accelerator can achieve. It tests quantum electrodynamics at field strengths approaching the Schwing limit. And it does all of this continuously, for thousands of years, without any intervention from us. All we have to do is watch. And that is perhaps the deepest lesson of the magnetar. The universe is not waiting for us to build the perfect experiment. The experiments are already running. They have been running for millions of years, in the cores of dead stars scattered across the galaxy. Stars that burned through their fuel, collapsed, and left behind dense remnants wrapped in fields of staggering power. Every one of those remnants is a message written in X-rays and gamma rays and radio pulses, carrying information about the behavior of matter and energy under conditions we may never be able to recreate. Our job is not to create these conditions. Our job is to learn to read the messages. A magnetar is a dead star. It produces no light of its own through nuclear fusion. It shines only because the magnetic field threaded through its impossibly dense matter is slowly, violently releasing the energy it stored at birth. The strongest fields in nature, locked inside 20 kilometers of the densest material in the universe, held in check by a crust that can resist almost anything, but not quite everything. When that crust breaks, the universe notices. Satellites detect the flare. The ionosphere of a planet 50,000 light-years away trembles. And somewhere on that planet, someone looks at the data and begins to understand, one measurement at a time, what happens when matter meets the most extreme fields nature has ever produced. That understanding is not complete. It may not be complete for decades or centuries, but it is growing, and every magnetar, burning quietly in the dark, is helping us get there.